And this lecture aims to provide a first intro to Bayes, which is a complex topic. If you have not been exposed to Bayes prior, I will say that it's something that rarely makes sense to anyone the first time they've seen it. But if it continues to not make sense after 3 or 4 exposures, let me know. And ironically, the more stats you've learned, the harder the transition to Bayes tends to be. So here's one of my XKCD favorite Bayesian comics. For years, we used to do a one-day workshop on Bayes before the Ecological Society of America meeting on the Sunday before. And I used to joke that my goal of that workshop was for people to get this joke. If you get this joke, then you understand enough about Bayes to get started. So, bit of motivation, why we care about Bayes, and some of this I said in my intro lecture earlier. Ecological data, epidemiological data are usually complex and violate the assumptions of classical tests. We have this need to update our forecasts as new data becomes available. We often deal with multiple sources of data and multiple sources of variability. And this complexity can be addressed with modern computational statistical techniques, Bayes in particular, but also many other. I'm a big fan of modern computational stats more broadly, not just Bayesian, as being able to handle the complexity of real-world data. So the first thing I want to do is introduce the idea of how we use models to, how we use data to judge between models. So imagine we have two forecasts. Forecast 1 representing hypothesis 1 that x is 0 with some uncertainty. Forecast 2 representing hypothesis 2 predicts x is 3 with some uncertainty. Our observation is exactly at 1.5. I've engineered this so it's exactly halfway in between. Your answer can't be whichever one's closer because it's the same. Which model is more likely to have generated this observation? Which hypothesis has more support from this observation than the other? So who thinks hypothesis 1 has more support? Who thinks hypothesis 2? Who thinks they're the same because it's exactly halfway? Nobody. Okay, so everyone thinks that hypothesis 2 is more compatible with this data. Why? Why do you think that? The area under the curve. Yeah, because that line is over that line, right? So that intuitive idea here, and we can put some numbers on this. You know, I can actually say, this is just our context, d norm for the normal density, this observation at 1.5 with alternative means and alternative standard deviations, and I can actually calculate what they would predict at each of these. You know, the density, you know, minus some integral over some delta x, 0.16 versus 0.06. So not only can we say that hypothesis 2 is more likely, we can actually say that it's approximately 2.7 times more likely because that's 0.16 divided by 0.06. Now, a difference of likelihood of 2.7 is remember even under frequentist approach, our standard of evidence is 1 in 20, 5%. That's a difference of 20-fold, not 2.7-fold. So we wouldn't actually reject either hypothesis, but we would say that one is more likely than the other. So the thing that we're doing there underlies a core statistical principle called the likelihood. And so to make that judgment there, we're using this idea of what's the probability of observing this data point given a specific choice of model, and particularly a particular choice of parameters for that model. So in that prior case, my models were simple. They were both normal distributions with a specific mean and a specific standard deviation. Models don't have to be complex, nonlinear, chaotic things. They can be simple. But in this case, we're using the data to judge which model is more likely. So the likelihood is the probability of observing a given data point conditional on a specific choice of parameter value theta. And the likelihood principle, which is a key statistical concept, is a parameter value is more likely than another if it is the one for which the data is more probable. Now, if you are a frequentist like Fisher, you would then derive all of our classic statistical estimators from this likelihood principle by saying, well, if I want to choose the one that's one parameter that's more likely than the other, I don't want the one that's more likely than the other one, I want the one that's most likely. So traditional stats takes the likelihood and maximizes it. Take the derivative, set it equal to 0, maximum. And if you do this for an ANOVA, a linear model, whatever, all of your classical textbook estimators come from taking this likelihood principle and trying to maximize it. So if we took, for example, linear regression, y has some intercept, some slope, and some epsilon, we can divide, so we can take this idea of a likelihood and split it into two parts, which we're going to call the process model and the data model. And so our classic regression model has a process model which is intercept plus slope times x, and has a data model saying that the error around that follows some normal distribution with some variance sigma squared. We can write this out mathematically. So I can take that normal distribution and convert those two things into a likelihood, saying the normal of my observations y is have a mean of, it's predicted by my linear process model, and this uncertainty sigma from my data model. I can then, and I have presumably more than one data point. So I take the product over all the data points. I can just take the equation for that and substitute that in, and now I'm starting to do math. And literally, if you take do this again, dl dA2, set that equal to 0, dl d sigma, set that equal to 0. Never forget about the sigma. That is a parameter. You have three equations and three unknowns. The rest is just algebra. And that's where, and I'm not going to do this. If I was doing this semester 1 course, I would actually go and derive regression, and this all just falls out mathematically nice, quick, and easy. So that's the concept of what a likelihood is. The key thing about bringing models and data together, though, is what do you choose for those things? The art, to kind of build on where we were just talking about, like how you build a model, is the choices you make about what we've been talking about up to in the last lecture, which is really how we build the process model, and then also how we choose our data model. So everything about how we choose our process model is everything we just talked about in the last lecture, and I want to talk a little bit about now, how do we choose the data model? So some key things you might think about when choosing how to model that data model, that probabilistic connection between your process model and your actual observations. What type of data is it? Is your data continuous? Is it integer or count? Is it Boolean? Is it some factor? Like, these are really basic things that should choose one probability distribution over another. So if you have categorical data, don't throw a normal distribution on that as your data model, because like, how would you calculate the residual between one category and another? Like, it doesn't even make sense. it won't work. There are distributions that do that. Another really common thing that I encounter in the types of models that we've talked about this week are range restrictions. Are negative values allowed? In particular, a key concept is a key distinction. Are negative observations allowed in the process model versus are negative observations allowed in the data model? There's lots of ecological processes where the process can't be negative, but the observation can, if the sensor is noisy. So you wouldn't want to restrict that away. But there are lots of things, like if you have count data, you can't count negative fish. Is there an upper bound? Are observed data near the bounds? So there could be, yes, fish can't be negative, but all my counts are like 10,000. So like, doesn't matter what distribute, like, I'm not near those boundaries. So dealing with, if there's a range restriction on your data and you are near that range restriction, getting that right can be really important in your data model. What process generated this data? So some sorts of data models are natural fits to certain types of processes, and the same, you can often write the same, what appears to be the same category of data and the same category of model can often have very different data models depending on nuances of how the data is generated. So I alluded earlier, I was originally trained as a plant ecologist. In particular, I worked a lot with forest data. If I want to measure, let's say I have data on how quickly trees are growing. Turns out there's a half dozen different ways to measure how quickly trees are growing, and they all imply different data models. I could take a tape measure and wrap it around a tree and measure the diameter, and I can come back next year and do the same thing. It's really easy to get negative data there just because of observation error. By contrast, I could install a band around the tree with a spring and measure how the distance in the band is growing. That data can't be negative. I could core the tree, measure the tree rings. That can't be negative. But it gives a different observation model than the dendrometer band. There's a whole bunch of different ways that the nuances, you really start thinking about the nuances of how the data, how the observations are actually collected when you think about how you write down your data model. And what distributions are appropriate descriptions of the data. There might be, you might be like, oh, like in concept, this is this distribution is a great representation of this process, data generating process. But if it doesn't actually fit the distribution of the data well empirically, who cares if it's a great distribution theoretically? So some things I think about, like here's an example. I have this table in this figure in my book, kind of showing a whole bunch of different distributions that have some common features. So like the top row are all discrete count data distributions that can't be negative. They all have slightly different shapes, represent slightly different concepts. The next row are all things that can go from negative infinity to positive infinity. All of these are things that are continuous but have to be positive. They can't have negative. And then they have some oddballs down here, things that have upper and lower bounds. Or this one is actually like these others in that it's zero bound, but clearly has a different shape. These are unimodal while this one is monotonic. But even if you conceptually are like, I have zero bound data and it's continuous, you're like, well, I have a whole bunch of different alternative choices. How do I choose which one? Sometimes you start with something that's, you make a choice and then you check your assumptions. Or you have a theoretical argument in favor of one. And if all else is equal, everything describes everything equally, you choose the one that makes the math easiest. Key point here, which I'll call resist the Gaussian reflex. Every stats textbook you encounter will throw a normal distribution on everything because it makes the math work out easier. There's weird theoretical arguments about the central limit theorem. So I think that's all bullshit. I think the arguments are, does it work well in practice? And actually, the normal does work well in practice a lot of time. And that's a better argument for why you should use it than any other thing. But don't just assume that the world is Gaussian until you've actually looked to see if it is. Okay, then how is the process modeled? I'm just going to throw out a whole gradient of things that builds on what we were talking about in the last lecture. A process model can be anything from a constant mean to like a highly mechanistic, dynamic, Earth system model. And from the statistical perspective, there's actually not much difference in how we would treat these things. We would still write down a likelihood around them and operate around that. So we talked about dynamic models as things evolve in time. We talked about linear models. We talked about some machine learning nonlinear model approaches. I'll talk more tomorrow about hierarchical models that allow us to capture variability in space and time. Okay, so likelihoods are great, but likelihoods by themselves have some limitations. So likelihoods are based on the probability of observing the data that we observed given some choice of model. That's what they are based on. Is that really what you want to know? You have your data. Why do you want to know about the probability of your data? Better question, wouldn't you rather want to know about the probability of your model conditional on the data? Because you're then conditioning on the thing you have and trying to make inference about the thing you don't have, which is your model parameters. Uncertainties. If I do this, write down the likelihood, take the derivative, set equal to 0, I get one answer. Maximum likelihood returns a point estimate, a single optimum, not a probability distribution. Frequentists can derive uncertainty estimates, obviously, but doing so requires making additional sets of assumptions. Sometimes those additional assumptions are straightforward, sometimes they're not. And sometimes different assumptions can lead to different answers. So as someone who does both frequentist and Bayesian stats, but tends to philosophically like Bayes, I like the fact that there's one way to get uncertainty estimates in Bayes. Well, when I teach maximum likelihood, there's like 4 or 5 different ways to get uncertainty bounds, and they don't all give the same answer. So bootstrapping versus Fisher information versus likelihood profiles, they'll all give you different estimates of what the uncertainties are because they all require making different additional assumptions. They're not built into the likelihood itself. And there's also the pragmatic one. If you're trying to optimize something, in practice, we're all lazy. We don't like writing, we don't like doing derivatives and solving things. We like asking computers to do this for us. Plus, you very quickly encounter problems where you can't analytically solve things. So we rely on numerical optimization, but numerical optimization has its own Achilles heels, which is when you have very many parameters in complex models, it can get stuck. Bayesian methods just in practice tend to be more robust. And this, I think, boils down to the key philosophical distinction between Bayes and frequentist, which I'll get into more. When you do this, you're not acknowledging that you may have prior information. So that whole idea of iterative updating, you can't iteratively update this solution. So you're making inference just using the data in hand. Whether that is a feature or a bug is the key distinction between whether you are a frequentist or a Bayesian. Frequentists think this is the problem with Bayes. Bayesian thinks this is the cool thing about Bayes. Okay, so to get to Bayes, I want to first do a little bit of math to make sure we're all on the same page about some key bits of notation. So this is the idea of joint conditional and marginal distributions. So to get these in your head, I'm just going to rely on a simple Venn diagram that happens to have 10 points in it to make the math work out easier. So joint distribution would be the probability of two things co-occurring. So if I want to know the probability of x and y, well, there's 3 things that are at the overlap of x and y out of 10. So there's the joint probability of x and y is 30%. If I want to know conditional probability, that's the probability of being in x conditional on, so this vertical line means conditional on, or often just said given y. So given that we're in the subset y, which has 6 points, the probability of being x is 3 out of 6, or 50%. And these things are not the same. The comma versus the line are really important. Joint, both, versus conditional, where you now say, I know this thing, and I want to make inference in this, versus I want to know about both of them jointly. And then marginal is just the probability of one of those things by itself. And marginal really gets its name from these ideas of contingency tables, where they really are the margins. So the probability of being x is the probability of being x given y, x given not y, and they add up to being the overall probability of x. So probability of x is 7 out of 10, because you can be x, you can be this half or in that half. And if you're dealing with continuous numbers, you would integrate these things instead of summing them. But here I'm just doing a sum because I'm dealing with discrete things. So I have margins in this direction, I have margins in that direction. Everything has to ultimately sum up to 100%. Cool. And these 3 concepts are related to each other. They're not, it should make sense. I mean, they're all derived from the same Venn diagram. So they all go together. And so the key relationship is to know that the conditional probability, the probability of being x given y, is the joint probability of being x and y divided by the marginal probability of being in y. I'm not going to derive that. Just take that as given right now. It's I find it easier to write this the other way, to get rid of the denominator and say the joint equals the conditional times the marginal. But the key point there being that there is this relationship between them, and particularly that that there's and if you plug in the actual numbers, you can check that this works out. You can pick any conditional probability and show that the math works out. And so if this is true and the marginal is just the integral of that, then the marginal is also the integral of that. This will just be a handy factoid that we'll use later. Okay. I'm now going to do a full derivation of Bayes' theorem. It takes about 3 lines. It's the only derivation I'm going to do all week. Okay. We have this relationship, joint equals conditional times marginal. I'm going to use in here x and theta as the 2 things I'm interested in. So I have the joint probability of x and theta is the conditional probability of x given theta times the probability of theta. We kind of have taken that as definitional. But joint, x and theta, does the order matter there? How is x and theta different than theta and x? It's not. So that means this is also true. Probability of theta and x is the probability of theta given x times the probability of x. If both of those things are true, I can set them equal to each other. And now divide by the probability of x. Ta-da, Bayes' theorem. So if anyone's ever heard that Bayes' theorem is controversial, No one disagrees about that derivation. That's not what people disagree about. Like, no one doesn't believe in Bayes' theorem. They just disagree about this guy over here. Again, whether it's a feature of the bug. So a key part of Bayes' theorem is that this likelihood part just showed up again, and it just showed up in the smack dab center of Bayes' theorem. So likelihoods never go away. Whether you're a frequentist or a Bayesian, you believe in likelihoods. And so we always need to be able to write down a likelihood, which again, we're going to split into our process model and our data model. Some description of how we think the underlying process is evolving, and then how that underlying process is related to the data that we actually observe. But now we have this iterative part that I was alluding to earlier, our probability of theta independent of the data. So we call this the prior because this reflects our understanding of theta before we see the data. And from that, we can then get our updated estimate of the probability of theta conditional on the new data we've collected. So this is where the iterative part comes in. We have our understanding of theta, we have some likelihood of encountering new data given that understanding of theta, and then it gives us an updated, we alluded to earlier, the thing we really want, the probability distribution of all the parameters in our model given the data we actually observed, which is an intuitive thing that we would want to know this. And what Bayes' theorem tells you essentially is that you can't go from here to here without that. So there's no way to go from a likelihood to a posterior without having a prior. You may have noted I've conveniently been ignoring the thing in the denominator there. Oh yeah, this was Bayes. Interesting factoid about Bayes. People think of Bayesian statistics as being kind of the new statistics because we only started being used in the last couple decades in practice. But all of this was derived by Reverend Bayes hundreds of years before Fisher. Like this is the old stats. Everything Fisher did was newer. Okay, but the denominator, remember the probability of x is just the probability, the marginal of the joint probability of x and theta, which is joint equals conditional times marginal. And I'll jump this to the next slide just to show that I can replace that probability of x in the bottom with this integral, which seems like, why would you do that? You just put an integral in there when we didn't have one. That doesn't seem to make anything nicer. But what it shows you is that the thing in the denominator is just a normalizing constant. It's just the integral of the thing in the numerator. And that ensures that this thing on this side is a proper probability. It ensures that this thing will integrate to 1. So a lot of times we don't even give this thing a name. Like the other parts, we all give them nice names. We don't give this a name because it's just a normalizing constant in practice. And because of that, we often drop it when we work with the math up until the very end when we then need to figure out what the normalizing constant is. It's not the interesting part. So that's our probability of model given data. Cool. So I'm going to give a couple quick examples of how we might actually apply this. So let's say patient has a disease that returns a positive, probably being positive given that you have the disease, 99%. The patient does not have the disease, the test returns positive at 5% of the time. Positive probability of positive. And I'm going to use exclamation as not disease. Background rate, base rate. 1 in 1,000 people have the disease. That sounds pretty common when you get down to it. Sorry. Oh, disease. Okay, but none of that's what we want to know. what you want to know is the probability that you have the disease if you just tested positive. Like, if you you don't actually want to know, if you're a human being, the probability that the test gives a positive given that you have disease doesn't matter to you nearly as much as the probability of you having the disease if you just tested positive. So how do we get to that? I mean, this is just Bayes' theorem. So to get from that to this, we need to know the prior, which is our base rate. So we have our posterior equals likelihood times prior, and then the bottom is just the integral of that. And since I only have two cases, I can write that out as a discrete sum. Before we do the math, this test is 99% accurate. You just tested positive. Should you be panicking? What do you think? Ballpark, for folks that haven't done the math. What do you think the probability of having the disease is given that you just tested positive without doing the math? Guesstimates, order of magnitude. 90%, 99%, 50%, 0.5%. Who thinks it's bigger than 50%? Plug in the math, about 2%. Big difference. And this matters. And what matters here is these false positives and the base rate. So in this case, the false positive rate is much higher than the base rate. This is actually why you don't test people for rare diseases unless they have pre-existing things that predispose them for that, because you're going to just see false positives. This isn't even rare. This isn't a 1 in 1,000, 1 in a million. This is a 1 in 1,000. It's not a 1 in a million. Yeah, so tests would have to be extremely accurate. That said, there's a 1 in 1,000 base rate. I'm now elevated to 19 in 1,000. So the probability that I have this disease just went up 19-fold. So you've moved in the direction suggesting that you do, but you have to acknowledge that base rate, that prior probability. So other XKCD, statistically speaking, if you pick up a seashell and don't hold it to your ear, you can probably hear the ocean. So you're starting to get the Bayesian jokes now. We're making progress. Okay, key part. Everything I did here with numbers also works with distributions in models. So if I have some relationship between some x and y, and I want to throw a linear regression at that, I can write down we had this on a slide earlier, our likelihood for a linear model, some normal for some vector of y's, some matrix of x's, some vector of betas. So this is just the matrix version of writing out linear regression. Our sigma, I have to have some prior probability on the sigma. What did I think sigma was before I observed the data? Some prior information about the betas, and some integral in the denominator, integrating all of that out. And I get posterior estimates of the intercept, the slope, and sigma. I actually get the joint distribution of all three, but it's hard to visualize a three-dimensional distribution. I'm visualizing the marginals of each of those, but you actually do get the full joint distribution of all your parameters from that. Cool. So how do you actually do that? Now that I show you that you can, and then that's just a Bayesian regression. we'll do this numerically after lunch. So before I get to how you do that, I'm going to give another example to kind of dive into how you might think about writing down a Bayesian model. And it's this kind of famous Bayes billiard table example. So imagine you are on one side of the table and there's a screen so that you can't see what's on the other side. You throw out one ball and you want to know where that ball is located kind of, you know, over this y dimension from here to the top of the table. When you just throw out the ball, I think we'd all agree that the ball is equally likely to be anywhere. So we're going to say our prior understanding, before we've collected any data of where that ball could be, is uniform. It's equally likely to be anywhere. So we've written down a prior distribution. We now want to update that with new information. And to update that, I'm going to throw out all the other balls. And I'm going to have someone on the other side that just tells me whether I'm to the left or the right of the ball that I threw out. In this case, there's 4 balls to the right and 11 to the left. Even without mathematically deriving the posterior, if you were on this side and couldn't see this, you'd be like, yeah, I'm pretty sure it's on this side of the table. But there's some probability that it's not, and I just happen to have all the balls end up on the left-hand side, just by chance, because with some probability that could have occurred. Okay, so how do we get to our posterior, the probability of probability of theta given y? So theta is the location of the ball, y are the discrete count data of those balls. So we need, this is uniform. What's the likelihood here? What's the data model for counting balls, counting billiard balls? So we go through the thing we talked about before. What do we know about the data generating process? What do we know about? So our first question, is the data continuous or discrete? Discrete. So that limits our number of distributions. And if you've not taken many stats courses, it's probably eliminated all the distributions you know about. Does anyone know any discrete distributions at all? Poisson is a discrete distribution. Binomial is another discrete distribution. Negative binomial is another. So who thinks that this counting of balls on one side or the other, throwing out a fixed number of balls, is a Poisson process or a binomial process? I heard murmurs of binomial. This is a great binomial process because we know the total number of balls that threw out, and we're just going to count y as, say, the number that landed on one side. And what we want to know about is that probability of ending up on one side or the other, which is determined by where the first ball went. Okay, so we can write this down. Binomial likelihood, uniform prior, integrating constant in the denominator. We can throw in some equations for that. Okay, what do I do with this? In some sense, I'm done. In a very other sense, you're like, okay. And this is the crux of why there was a multiple 100-year gap between the derivation of Bayes' theorem and its practical everyday application. Because it's really easy to do this. It's really hard to know what to do with it next. In particular, what if I wanted to know the mean of that distribution? That seems like a very obvious thing I'd want to know first, which is I now have a distribution that describes my posterior. Where's the mean of that? Well, if you remember how to estimate a mean, you do an integral of x px, or in this case, integral of theta p theta given y p theta. But that is that whole equation, which also has an integral in its, oh my God, there's an integral and denominator inside an integral. This seems hard. Yeah, that's why people didn't do it, because it seems really hard. And if I want to know the variance, then I have to do the integral of okay, just to get the variance. That's just to get the first two moments. I'm now doing multiple horrible integrals with other integrals inside their denominators. So what do we do in practice? Well, we hope we get lucky. We hope that this thing looks like something else we already know. And in this case, that thing up there looks a lot like this thing in here, where I'm going to call theta x and y alpha minus 1 and beta minus 1 matches to n minus 1, and it all just works out. And so if the math works out really well to be something you already know the answer of, then you're great, because someone else did the hard work of figuring out all the moments of this distribution. And there's a function in R that'll plot it for you and you're done. So the practical answer is, if you're lucky, the math works out, and if you're not, you have to find another solution. Okay, before I get to the other solution, things to note. This posterior is a proper full probability distribution. This theta is a random variable. It's something that is known with uncertainty, and what we're interested in when we're doing Bayesian inference is this full distribution. It's also worth noting that y over n, which would have been our frequentist estimator of the posterior mean, is actually slightly different than the true posterior mean, because the prior does have information. The prior mean was 0.5, and so our posterior mean does combine the prior and the likelihood. That's not a bug, that's a feature. Another thing that's useful to note about this is when I did that solution, I plugged in the final number of balls, I threw in the final number that ended up on one side, and I got an answer. I said Bayesian inference can also be done iteratively. If I started with that prior and then just observed one ball and got a posterior, and then I threw out another ball and used the first posterior as the prior and updated it, I could do that. I could imagine I'm throwing out balls one at a time, and I'm updating my information one ball at a time using the posterior from one step as the prior for the next. And I am guaranteed mathematically to have the same answer as if I had analyzed the data all at once. So it doesn't matter, iterative update conceptually. In terms of mathematical implementation, you can get rounding errors and stuff like that. So they're not always exactly the same, but conceptually they should give you the same answer, whether you're updating iteratively or whether you analyze the data all at once. So to give another quick example, one that's really very common, let's say I have just a simple normal mean and variance. So I have some data set Y that I want to estimate the mean for. And I'm using proportional and getting rid of the normalizing constants in the normal because they're normalizing constants. They end up in the denominator in the integral. We're not worrying about them. I'm going to say use a normal prior on this. So here's, in the likelihood, the thing I'm trying to make an inference on is on the right-hand side of that conditional. On the prior, it's on the left-hand side, so these things match up. Likelihood times prior is what I'm going to want to do mathematically. Yeah, mu0 is my prior mean, tau is my prior variance. So multiply those things together, write out their equations, put them together. I will stop doing the algebra at this point. You may recognize what's inside these parentheses as completing the square, and remember that the word completing the square is something you've heard of, and you've probably, with my prior probability is 99% of you have forgotten how to complete a square, but remember the words completing a square. But the point is you can do that math. It's just a bunch of algebra, and you, in this case, end up in one of those situations where the answer looks like something you know. Normal times normal gives you a normal. But it's a little ugly. We have everything here is your mean, everything there is your variance. I'm going to make a quick substitution that's very common in Bayesian stats when working with the normal, which is this idea of a precision. A precision is 1 over variance or 1 over standard deviation squared. Bayesians like precisions because they make the math look cleaner. So if I use S as 1 over sigma squared and T of 1 over tau squared, this simplifies to something that's much more interpretable, saying that my posterior estimate of the mean, given the data, has a mean that is a weighted average between the data and the prior, each weighted by the precisions. So S over, so the observational error in the data versus the prior precision, sorry, the prior precision and the data precision. And then again, here, this is weighted by the prior precision. So weighted average between the prior and the data. And then my posterior precision is just the sum of the two precisions. The precision coming from the likelihood and the precision coming from the prior. That is an exact answer for the normal distribution, the weighted average of the prior and the likelihood, and then the precisions are the sum. Conceptually, most Bayesian inference answers are very similar conceptually, if not identical mathematically, that anytime you combine prior information with new information, it's some sort of fusion of the two weighted by their uncertainties, and that the precision of the posterior is always greater than the precision of the likelihood or the data. So we always get more precise by fusing the prior with the likelihood. And we'll see that solution again when we start talking about iterative updating tomorrow. Okay, what if we can't solve this analytically, which ends up being 99% of all Bayesian inference, if not more? So the key advance in Bayesian stats that happened in the 90s was the advent of practical numerical methods for doing Bayesian inference. There'd been some impractical numerical methods before that, like brute force numerical integration, which, you're substituting having to do an integral and denominator with having to do numerical integration, which isn't any fun either. Okay, so what we want to do is just set up what we want to do here. What we want to do isn't what we did with the likelihood. We're not trying to optimize this. We want to actually solve for a distribution. We have this need to deal with integrating the denominator, and we want something that's going to give us a way of easily not just getting the posterior, but information about the posterior. Because once you have the posterior, you're going to immediately start asking questions like, what's the mean, the median, the mode, the variance, the quantiles, confidence intervals, et cetera. These are the practical things you do with distributions once you have them. So something that requires me then doing more integrals isn't going to be very helpful. So the key idea, key bit of insight is that you can approximate any distribution with samples from that distribution. So if I take enough samples from the posterior distribution, I can approximate the distribution with the histogram of that distribution. If I want to know the mean, I can just calculate the sample mean. If I want to know the variance, I can calculate the sample variance. If I want to know quantiles, I can just count up. If I want to know confidence interval, I can say I want 2.5% of the samples over here and 2.5% over there, so I have 95% in the middle. That's really easy to do. Like, you don't have to do an integral. You just have to say, like, sort them in order and get rid of 2.5% on each side. Super easy to do. So the idea is, if I can take samples from a distribution, then I can calculate anything I want from it really simply, and I can approximate it, and I am great. And the completely unintuitive thing about Bayes is it turns out that we can sample from distributions even when we can't write them down. And that's the beauty of this. That's what's going to make this work, is we're going to show there's a whole this is kind of the guts of like the art of Bayes, is like that there's whole classes of algorithms that allow you to sample from distributions that you can't write down in closed form. And that's going to be how we're going to do this. And we're going to rely on probably the biggest workhorse in Bayes. There's lots of algorithms. We're going to focus on one, which is called Markov chain Monte Carlo. It's the one built into most numerical methods. There's some bells and whistles on some of these sometimes, but the basic idea is you start from some initial guess of what your parameters. You need some place to start the algorithm off. Worth noting that if you're doing numerical optimization in likelihood, you need an initial guess as well. So in any numerical method, you need some place to start. Doesn't really matter what it is. We'll call that theta. We're going to now calculate the unnormalized posterior. That's likelihood times prior. We're going to ignore the denominator integrating constant for now, because it turns out it's going to cancel out. Probably y given theta, probability theta. And then we're going to propose a new parameter value. Turns out it doesn't really matter how we propose it. Theta. The algorithm isn't that sensitive to how you propose it. We're going to calculate a new unnormalized posterior. And then we're going to decide whether or not we like this new value better than our current value or not. And we're going to do that probabilistically. So the probability of accepting this new parameter value is going to be the ratio of this, the unnormalized likelihood times prior times the original likelihood times prior. And if I'd included the normalizing constant in here, they would have just canceled out, which is great because all that ugly integral in the denominator just canceled out. It went away. It was wonderful. And this is simple. So if the new value is better than the current value, this number is going to be bigger than 1. You're going to always accept a better value. But you're going to accept worse values probabilistically. You're going to flip a coin. And sometimes you're going to move in a direction that makes the parameter values worse. Sometimes you're not. If two values are very similar, you're going to move between them very often. If one value is really worse, you're not going to go there very often. And you're going to repeat this. I'm going to keep proposing new values and accepting and rejecting, and then proposing new values and accepting and rejecting. In numerical optimization, you're trying to like go down and find the best value. In MCMC, there is no best. You just keep doing this to generate samples. You do this until you have enough samples to draw that histogram and calculate those moments. I would say back of the envelope, about 5,000. Yeah. So here's a simple example, and we'll do this more in practice. So imagine after lunch, imagine I have a prior with a mean of 53 and a variance of 10,000. I observe one data point. I'm going to estimate a mean and variance with one data point, because if you have a prior, you can do that. I'm going to say a known variance, and I'm going to start from what are called chains. I'm going to repeat this 3 times, starting from 3 different places to check whether I end up in the same place. And this is one of the things that's very common in all numerical methods. Everyone tells you to do this in numerical optimization, and no one does. In MCMC, everyone always does this. You always start the algorithm from different places to ensure that they end up in the same place. I'm going to start at minus 100, 0, and 100. Okay, so here's 10 iterations of this algorithm. Here I'm proposing a new value, deciding to accept it or not. There's a little wiggle there, there's a little wiggle there, but mostly I'm not accepting new values very often. I actually chose values to make the proposal very unsuccessful, just to make this visually illustrative. I'll keep running this. Now I've run this for 100 time steps. You can start seeing wiggles in there where it sometimes, you can see it tends to move towards, remember the data point was at 43. It tends to, you can see it actually does move in the other direction once in a while, but it's tending to move together. Now I've done 1,000 time points, and they're all in the same part of parameter space, which is good. And I'll keep going. And this is what MCMC looks like. So you've got some initial period that's dependent upon your initial conditions, and we call that the burn-in. We throw that out. Because that's just kind of some initial numerical burn-in where the algorithm's trying to find where it wants to be in parameter space. It's now what we call, this is converged. These three chains have all converged to the same part of parameter space, and now they're just generating samples from that part of parameter space. So if I take all those samples and draw a histogram, I have an approximation of my distribution. So in this case, there's actually a known analytical solution. We got pretty darn close to it. And if I check the moments, I can show that I'm very close to that as well. And the nice thing that we'll discover after lunch is there are multiple numerical packages designed to make the implementation of these algorithms fairly straightforward, to allow you to write down your likelihood, to write down your priors using a bit of code, and then these languages, some of you will use JAG, some of you use Stan. They will interpret that model you've written down, decide how to sample it, and then actually go through the numerics of doing the samples, and you get something like this out at the end where you need to figure out how much burn-in to throw out, and then perform some summary statistics on what's left. A couple things to note. In MCMC, unlike most everything else you do in statistics, data that output that looks like white noise is like perfect. It's the only place in science where like noise is what you're looking for. If you see things that are not converged, that's where you have issues. One of my postdocs loves calling this the fuzzy, former postdocs, the fuzzy caterpillars. When when your MCMC output looks like fuzzy caterpillars, you're golden. And like I said, I actually, if you implemented this problem in JAGS or Stan, it would have actually converged in about 5 steps, and it would have sampled way more efficiently. Actually, to be able to see what it's doing, I made it mix slowly. In practice, it's faster than that. Cool. Some quick advantages. So it is multidimensional. So like it's important to remember, and people often forget this. The output, the posterior from Bayes' theorem, is the joint distribution of all of your parameters. You often visualize, like if I do a regression, I'm going to look at the slope and intercept and sigma, but I'm actually going to get the joint distribution. So if I look at the posterior, and you guys will see this after lunch. If I look at the joint distribution of my slope and the intercept, I actually have a joint distribution with some non-trivial covariance structure. That covariance structure is there in classic regression as well. You just don't see it. And this makes sense because if I have a cloud of data and I want a line to go through the cloud, if I make the intercept higher, I have to make the slope shallower to still go through the same cloud of data. So you get this joint distribution of the two, which will actually mean that you know more. You actually know more things about your parameters than just their marginal distributions. But you get that too. Like you can draw a marginal there, you can draw a marginal there, calculate means and confidence intervals and all that stuff. It is actually, when you get down to it, a pretty simple algorithm to implement. You need to be able to propose new parameter values, and then you need to be able to calculate that likelihood in prior, and then you need to be able to flip a coin, but whether you accept or not. And it is remarkably robust. Because you accept values that go in the wrong direction, probabilistically, MCMC is really robust to not getting stuck in local minima It can, which is why you run multiple chains and check that they end up in the same place, but it tends to be much more robust. I mean, I've had multiple real world problems where I was like, oh, I'll just do this in maximum likelihood because it'll be quick and easy. And then try like 7 different numerical optimization algorithms, all that give me different answers. And then I just go back to MCMC, which every time I run it always gives me the same answer. I'm like, I should have just done this first case. Some disadvantages. Sequential samples are not independent. So when I do this sampling, the value sample at 2000 and the value at 2001 are going to be really similar. So the effective number of samples you have is going to be less than the actual number of samples you have. We'll go over this in the after lunch, that we can calculate what's called the effective sample size, and it's the effective sample size that you need to get to around 5,000. And the more autocorrelated your samples are, the longer you have to run MCMC in practice. So in practice, sometimes to get 5,000 independent samples, you need to run 100,000 steps, or even 1,000,000 steps if you're really unlucky. That can be computationally intensive, especially if your models are big or your data is big. You have to discard this burn-in before convergence, and then you have to assess convergence. So, whenever we fit a model, there's model checking. So we'll look at the residuals and QQ plots and all that stuff that you've learned before. There's this extra step in Bayesian inference that you also have to check that convergence occurred. Because if you start doing those other things before checking for convergence, like you might not have an answer yet. Okay, so the last little bit I'm keeping you from lunch is just to say a little bit more about priors, because they are the feature of the bug. They are what make it possible to calculate posteriors rather than likelihoods. They do provide us this way of doing iterative inference. But where do priors come from? So if you look in most stats textbooks, they choose what are called uninformative or vague priors. They choose priors that have very little information content to them. So, mean of 0 plus with a variance of 1,000,000. Why do they do that? Because they're statisticians. They don't know your system. How do they know what the right answer is? They chose, just because you see a lot of vague or uninformative priors in the stats literature doesn't mean that you should use vague or uninformative priors. It just means that statisticians don't know your own system. If you know your study system, using informative priors can be really, really helpful. So where they often come from, they can come from previous analyses, this iterative updating. They can come from the literature. In a lot of the model calibration I do formal meta-analyses to estimate my priors, and they can come from expert knowledge. There are ways of doing expert elicitation to estimate probability distributions from expert knowledge and use them as priors. I could do a whole lecture on that. If anyone's interested, I'm happy to talk more about that. Where they cannot come from, this is in orange because it's important. Where they cannot come from is the data itself, because remember, the prior represents our estimate of that thing before we see the data. So if I have some data set X, I can't use the mean and variance of X to set the prior on the mean and variance of X, because I've now used the data twice. It leads to falsely overconfident results. So that's the only rule. Priors can come from anywhere except the data. So the subjective part that frequentists don't like is that two analysts given the same data could choose different priors. But in practice, 2 analysts given the same data could also choose different process models. There's a lot of subjectivity in what we're doing regardless. If two Bayesians choose uninformative priors, they're probably not going to get really different answers. If one of them is an expert in that area and really does have prior knowledge, great. I would say use it. Science is not in a vacuum. If you knew beforehand, like the base rate example, if you knew beforehand that the base incidence of this disease is 1 in 1,000, don't throw that information out. It's critical to getting the right answer. And then how you chose a distribution for that, it's basically analogous to choosing the data model, thinking about range restrictions, shape, etc. And then there's this other thing called conjugacy. Conjugacy is basically when the likelihood and the prior go together to make a distribution we know the name of. So modern computational techniques do not require conjugacy, but all else being equal, things will go smoother if you do choose conjugacy. So like if I'm, I'll give an example. If I want to put a prior on a variance, and I know that variances can't be negative and they're continuous, and I showed you I showed you a y-bol, a gamma, a log normal, a chi-squared, and if I then put a normal likelihood, for some of those choices, the math is going to get really ugly. And so for some of those choices, the math is going to work out perfectly. So if you have no a priori reason to choose between those, choose the one that makes the math work out. But if you have any reason to choose a specific distribution, do it. The numerical methods will work. They just might need to take a few more samples. Okay. And here's a couple other resources. I've kept you 5 minutes past lunch, which makes me evil. But I'm happy to answer any questions. There should be a bajillion. And we also have time after lunch during the hands-on as well. You had a question.
I feel like maybe I understand it correctly, but it doesn't seem to matter that much what prior you put in, because it will eventually occur in some states regardless. So yeah, I guess the question is, how important is it?
How important is choosing the right prior? So the intuition that if you have enough data, the likelihood should swamp the prior is a good one. That's going to apply almost all of the time. So priors matter much more in data limited cases. So if you were dealing with, week 1 of an emerging infectious disease, priors matter because they're going to represent what you knew independent of the data. Year 1 of an invasive species, priors are going to matter. Satellite remote sensing, priors don't matter. You've got 50 petabytes a year of data. The exception being if priors impose range restrictions, then those range restrictions will be reflected in your posterior regardless of how much data you have. So if I have a prior that says, the mean has to be between 0 and 10, and all my data is at 1,000, the mean's going to end up as 10. Because your prior says the mean can't be bigger than 10. So the priors do matter, and uniform priors tend to be bad choices because they have those sort of discrete edges. Yeah, and you like what I'm saying. When you look at the stats literature, you see a lot of choices of uninformed priors because they're statisticians, they don't know your system. You see a lot of ecologists and epidemiologists mimicking statisticians because they see that in the literature and think that's what you're supposed to do. That doesn't mean it has to be. So I don't know, I think it was in my earlier slide. If I am doing iterative forecasting and my prior is yesterday's prediction for what's going to happen today, which is fairly informative because I spent years building a process model predicting what I thought was going to happen today given what I observed yesterday, and today's observation is noisy, my posterior is mostly going to look like my prior. So in forecasting in particular, to give away a key concept of forecasting is that your forecast is your prior because it represents what you know about the system before you observe the data that hasn't happened yet. And Bayes' theorem allows you to do this iterative updating. And so in forecasting in particular, you tend to work with informative priors way more than you do with standalone data analysis. In fact, that's key to the whole idea of iterative updating, is that your prior embeds every piece of data you observed before today. Because what if it didn't? Could you imagine how numerical weather forecasting would work if I had to assimilate every observation that has been made about the atmosphere from 1955 to today in order to predict the next 6 hours? It doesn't work. That's why we rely on iterative updating, because once problems get big, it's the only way to do them in practice. I know.